Unit Overview. In this unit, we study an important data structure called graph. A graph is a versatile and flexible structure. It can be used to represent complex relationship among the elements of a data collection. The relationship can be nonlinear and of different types, such as one-to-many, many-to-one, or many-to-many. Because of these characteristics, graphs are often used for modeling and simulation applications, not only in computer science but also in other disciplines. The unit begins with an introduction to graph terminology and an overview of graph applications. It then discusses various ways of representing graph and associated operations for manipulating graph data. In particular, the graph traversal methods known as depth-first search and breadth-first search are explored together with their implementations. The unit concludes with the description of important graph algorithms attributed to Dijkstra, Prim, and Cruxal, which are commonly used in graph applications. Objectives. After completing this unit, you should be able to describe basic terminologies and concepts about graph data structure, learn about common graph applications, understand the main operations associated with graph data structure, understand the implementation of graph methods for matrix representation, represent a graph using adjacency matrix, learn about the significance of path matrix and different algorithms for computing path matrix. Describe the algorithm for determining shortest path matrix. Understand linked list representation of a graph. Describe the depth-first and breadth-first search methods and their implementations. Understand Dijkstra algorithm for finding minimum traversal cost for a graph. Use Cruxal's and Prim's algorithms for finding minimum spanning trees. Learn about topological sorting. Introduction to graphs. Graph is a data structure that has been a subject of intensive study over the past several hundred years. Famous mathematician Euler is credited with doing pioneering work on graph theory. Using a graph representation, he was able to solve the celebrated problem of crossing 7 bridges to the island of Königsberg without using any one of the path more than once. However, many of the important and useful graph algorithms have been discovered over the past 4 decades, almost in parallel with the advent of computers. Unlike other data structures, graphs are often studied as mathematical constructs. As such, much of the terminology and notions associated with graph data structures are borrowed from the discipline of discrete mathematics. In this section, we examine the relevant definitions and concepts. Graph. A graph is a collection of data items called vertices and edges. Vertex stores some kind of data. An edge represents a connection between pairs of vertices. A vertex is sometimes referred to as node or point. An edge is also termed as arc. Suppose A and B represent a pair of vertices in a graph. The edge connecting A to B can be represented as AB, or more commonly as enclosed in a pair of parentheses. In formal theory of graphs, set notation is often used to represent a graph and its associated elements. Thus, a graph G is defined as a set VE, where V is a set of vertices and E is a set of edges. If V1, V2, V3 up to Vn are the vertices, Then using set notations we can write. More often, graphs are shown pictorially using diagrams. Typically, a rectangle, oval, or circle represents a vertex. Lines or arcs are used to depict the edges. Suppose, for example, a graph consists of vertices A, B, C, D, and E with edges AB, AC, BC, CD, CE, DE. Figure shows a diagrammatical representation of this graph. It is emphasized that in pictorial representation, the location of vertex is immaterial for some applications. Thus, vertices can be laid out in several ways. For example, this figure is an alternative representation with a different geometrical configuration of the same set of vertices and edges. Although these two pictorial representations give different looks, they represent the same set of data elements in the graph. Graphs are classified on basis of properties of the edges and their orientation. The major categories are undirected, directed, weighted, and multigraph. We now briefly overview the salient features of each type. Undirected graph. In an undirected graph, the edges are not assigned any direction. Thus, there can be at most one edge between a pair of vertices. The undirected graph is used to represent one-to-one relationship among the data elements. Figure shows an example in which all elements are linked together. It can be shown that an undirected graph with n vertices can have at most n into n-1 by 2 edges. The edges of an undirected graph are denoted by unordered pair of vertices enclosed in parentheses. For example, an edge connecting vertices V and U is represented as UV. Note that UV and VU represent the same edge. An undirected graph is also termed as undigraph. A graph in which all the edges are present is called complete graph. By contrast, a graph with comparatively fewer edges is called sparse. Generally, a graph with less than n log n edges, where n is the number of vertices, is categorized as sparse. Directed graph. In a directed graph, each node is assigned a direction. The edges of a directed graph are usually denoted by an ordered pair of vertices enclosed in angle brackets. Thus, the pair UV represents an edge which starts at vertex U and ends at vertex V. The first vertex is referred to initial vertex and the second as terminal vertex. As such, UV and VU represent different edges connecting the same pair of vertices. A directed graph is also termed as digraph or network. Figure shows an example of a directed graph. It consists of vertices A, B, C, D, and E, and edges AB, BA, AD, ED, CB, DC, and ED. Weighted graphs. In weighted graph, the edges are assigned data values referred to as weights. Weighted graphs have several real-life applications. A weighted graph might, for instance, represent cost of transportation between two locations, amount of data traffic between workstation in a network, or distances between two cities. Figure shows an example of a weighted graph. The numbers attached to the edges are the weights. A weighted graph can be directed or undirected depending on the nature of application. For example, a weighted directed graph can represent flight journey between two airports because flight distances between two airports might be different depending on the flight paths for forward and backward journeys. Multigraph. A multigraph is a generalization of a directed graph. In their structure, there can be multiple edges between a pair of vertices. Such edges are termed as parallel edges. Figure shows a multigraph. Observe that there are three edges between the vertices A and B. There are two parallel edges from A to B and one edge from B to A. A multigraph is used to represent a many-to-many relationship among graph elements. Graph paths. A path between a pair of vertices is a sequence of vertices in the graph which are connected by successive edges. We can denote the path by enclosing the list of vertices in a pair of angle brackets. For example, in figure, ABDE represents a path between the vertex A and E. The length of a path is the number of edges that occur along the path. For example, the length of path ABDE is 3. The vertices which have path of length of 1 are called adjacent vertices or neighbors. For example, in this figure, vertices B, C and D are neighbors of vertex A. A vertex is said to be reachable from another vertex if there exists a path between the vertices. In the figure, vertex B is reachable from vertex A or vertex E, but A is not reachable from any other vertex. Loops and cycles. Two special paths termed as loop and cycle are important in graph applications. A loop is an edge that begins and terminates at the same vertex. Figure shows an example in which vertex A and C have loops. A cycle is a path that originates and terminates at the same vertex, but unlike a loop, a cycle includes more than one vertex. Figure shows a graph with a cycle represented by the path ADCA. Another cycle is ABA. In an undirected graph, the path between a pair of vertices cannot be called a cycle because backward and forward traversals are along the same path. In an undirected graph, a cycle must involve at least 3 vertices as shown in figure. A graph that does not contain any cycle is called acyclic. Simple path. A graph path in which all vertices and edges are distinct is called simple path. In a simple path, repeated vertices or edges are not permitted. Sometimes a distinction is made between simple path and elementary path. In an elementary path, repeated vertices are permitted along the path. Figure presents simple and non-simple paths in a graph. The path A, E, B, C, E, D from A to D is non-simple because vertex E is repeated along the path. On the other hand, path AED is simple. Graph connectedness. A graph is said to be connected if there exists a path between all pairs of vertices. In other words, each vertex is reachable from any other. Connectedness in an undirected graph is simple because the edges can be traversed in either direction to reach a vertex. Figure shows a connected undirected graph. Observe that there is no direct connection between the vertices B and C. However, C can be reached from B via vertex A. Connectedness may involve paths of length greater than 1. In a directed graph, connectedness is more complex. For example, a vertex A may be connected to B, but B may not be connected to A. A graph is called weakly connected if one or more vertices are not reachable from any other vertex. Figure shows an example of weakly connected graph. Observe that vertex A is not reachable from any other vertex. A graph is termed unilaterally connected if at least one of the vertices in a pair is reachable from the other. Figure shows a unilaterally connected graph. For example, A is not reachable from B, but B is reachable from A. Likewise, B is not reachable from C, but C is reachable from B via D. A graph is called strongly connected if, for all pairs of vertices, both vertices are reachable from either of the vertex. In other words, if A and B are any arbitrary vertices, then A must be reachable from B and B must be reachable from A. Figure shows an example of a strongly connected graph. Consider, for example, the pair of vertices A and D. Observe that A is reachable from D via C and D is reachable from A via B. You can verify that every vertex is reachable from any other vertex. Degree of vertex. The number of edges that connect a given vertex to other vertices is called degree of the vertex. In a directed graph, the number of edges that originate from a vertex is called out degree. Likewise, the number of edges that terminate on vertex is called in degree of the vertex. The in and out degrees of the vertex V are denoted by the expression. Consider, for example, the graph shown in this figure. It can be verified that in degree of A is 2 and out degree of A is 4. The in degree of E is 2 and out degree of E is 0. Application of graphs. As noted before, a distinguishing feature of a graph data structure is its ability to represent complex relationship among data elements. In general, a graph can be used to represent a structure in which many-to-many type relationships exist among the data elements. In real life, we come across many such examples. Some familiar examples are computer networks, electrical circuits, transport networks, assembly lines, molecular structures, and databases. In computer networks, workstations and servers can be viewed as vertices and links between the devices as edges. Thus, a graph may be used to configure a network for optimum performance. For example, using appropriate algorithm, we can determine the shortest or most economical routes for dispatching packets of information along different paths in a network. Electronical circuits are another common example of application of graphs. Connectivity and performance of a circuit can be ascertained with the help of graph theoretical methods. Graphs are also useful to schedule various tasks in an assembly line of an industrial plant when certain tasks must be completed before the next task is started. The most familiar examples of graphs applications are found in transport industry. For example, airport, cities, and other sites can be represented as vertices, and the air routes, railway lines, and roads as edges. A graph can be used to answer such questions as Is there a connection between two given locations? If so, what is the minimum cost of transportation? Or what is the shortest route? In plain words, one may want to know a travel schedule with minimum travel time or minimum fare between any pair of cities. Several graph algorithms exist to solve such problems. Graphs are also useful in studying molecular structures. The graph-theoretic methods can be used to differentiate between structures with different configuration of a set of molecules. Finally, in a database application, graphs are frequently used to represent various types of entity relationships, often referred to as ERD diagram. Operation on graphs. As with other data structures, we can perform several operations on graphs to access the data elements and update the information contained in the graph. We can also modify the relationship among data elements. Some useful common operations include the following: inserting a new vertex into the graph, removing an existing vertex, inserting a new edge between a given pair of vertices, removing an existing edge, determining degree of a vertex, determining reachability of a vertex, finding paths of different lengths between a given pair of vertices, determining the shortest path between a pair of designated vertices, traversing a graph. We shall examine the implementation of these methods while studying different ways of representing graphs. Matrix representation of graph. We have seen that a graph can be represented diagrammatically with direction of edges shown explicitly. However, pictorial representation is not useful for analytical studies of a graph. Further, the pictorial representation is not feasible when a graph contains a large number of vertices and edges. There are alternative ways of representing graphs. Two common methods are known as matrix representation and list representation. The choice depends on whether the graph is dense or sparse. We first look at the matrix representation. In matrix representation, the edges between the vertices are represented as elements of a matrix called adjacency matrix. The rows and columns of the matrix are labeled by graph vertices. If an edge between a pair of vertices exists, then corresponding row and column contains 1 and 0 otherwise. We can algebraically define an adjacency matrix by using matrix notation. If Aij is an element of a matrix A in ith row and jth column, then Aij equal 1 if there exists an edge between ith and jth vertex, Aij equals 0 otherwise. Consider the graph shown in figure. It is a directed graph with vertices labeled A, B, C, D, E, F. This figure shows the matrix corresponding to this graph. Since in some programming languages such as C, C++, integers 0 and 1 refer to logical false and true values, the adjacency matrix is sometimes referred to as Boolean matrix or bit matrix. An adjacency matrix that contains the weight associated with edges of a weight graph is called weight matrix. A major advantage of matrix representation is that we can determine the degree of vertex easily by simply summing the entries in the corresponding rows and columns of the adjacency matrix. For example, consider the vertex D. The sum of values in the row corresponding to the vertex is 2. We conclude that out degree of D is 2. Also, the sum of entries in the column corresponding to D is 3. So, the n degree of D is 3. By looking at the pictorial representation in figure, you can verify that 2 edges originate from D and 3 edges terminate at D. Another advantage of the adjacency matrix is that insertion and deletion of edges can be accomplished easily. In order to remove an edge, we simply toggle the value 1 to 0 in the corresponding row and column. The biggest advantage of matrix representation is that we can compute path length by performing basic matrix operations. We shall look at this aspect later. A drawback of matrix representation is that insertion and deletion of new vertices involves complex procedures. To insert a new vertex, we would need to add a new column and a new row. Also, the columns and rows would need to be shifted to place the new vertex in proper location. In order to delete a vertex, we remove the corresponding row and column from the adjacency matrix. However, after removal of matrix elements, we would need to shift the succeeding rows and columns to update the adjacency matrix. This is a time-consuming operation, particularly if column or row to be deleted happens to be towards the end. Another drawback of adjacency matrix is that it results in uneconomical utilization of storage space when the number of edges is small compared to the number of vertices. In such a case, the adjacency matrix would contain a large number of zeros and would be sparse. Consider, for example, a graph consisting of 10 vertices with 4 edges. The adjacency matrix would contain 100 entries with only 4 ones. Thus, 96% storage space would be wasted. This drawback is overcome in a list representation of a graph. Click here to watch visualization of adjacency matrix. Array-based implementation of graph. We have seen that a matrix is analogous to a two-dimensional array. We can therefore use the two-dimensional array to store the elements of an adjacency matrix. We also use a one-dimensional array to store information contained in vertices. Therefore, in order to implement graph's data structure, we define a class which consists of 2 arrays and includes associated graph operation. We call this class graph matrix. The structure of the class is shown in figure. It consists of following arrays: two-dimensional array E to store edges, one-dimensional character array V to store vertices. The basic operations are implemented using the following methods: add vertex to insert a new vertex, add edge to insert a new edge, del edge to delete an existing edge, display to print the graph. It is assumed that vertices store single characters. The edges are represented by n into n matrix. The actual codes for the class methods are given in the demonstration. Click button to run the array-based implementation of a graph. Path length in a graph. The adjacency matrix shows whether or not a path exists between a pair of vertices. In other words, it tabulates all paths of length 1 in a graph. In some applications, we are interested to know whether there are paths of length greater than 1 between a pair of vertices. Consider, for example, a simple graph shown in this figure. Note that vertices A and B are connected to vertex C, but it is not directly connected to B. Therefore, although there is no path of length 1 between A and B, there is also another path of length 2, because B is reachable from A via C. Using adjacency matrix, we can find paths of different lengths for a graph. It can be shown that square of the adjacency matrix gives paths of length 2. If A is an adjacency matrix with element Aij in ith row and jth column, then the element Bij of the A square are given by the following formula for the matrix multiplication, where sigma denotes sum obtained by varying k from 1 to n. Here, n is the number of vertices. The formula is based on the preceding observation that if a path exists between the ith and kth vertex, and there is path between kth and jth vertex, then there is a path of length 2 between ith and jth vertex. Consider, for example, the directed graph shown in figure and associated adjacency matrix A. Next figure shows the square of A. From the matrix A square shown in the figure, we can conclude that there is one path of length 2 between A and C. This is, in fact, the path ADC. Also, there are two paths of length 2 between D and E. These are DAE and DCE, shown with bold arcs. It can be shown that if A is the adjacency matrix, then in general A raised to the power n represents the number of paths of length n between different pairs of vertices of a graph. For example, a cube would tabulate the number of paths of length 3. The elements of the cube of adjacent matrix A are given by the formula, where Pij refers to an element in the ith row and jth column of matrix A cube. In other words, Pij is the total number of paths of length 3 between the ith and jth vertex of a graph. This figure shows the graph matrix A raised to power 3. The matrix indicates that these paths are CDAE and CDDE. The first is a simple path since no vertex is repeated along path. The other is non-simple because vertex C is repeated. Click here to watch computations of path lengths. Path matrix. A path matrix for a graph shows whether or not a vertex is reachable from a given vertex, irrespective of the path length. In other words, a vertex A would be reachable from B if there exists a path of any length. A path matrix is a special matrix that tells if there is a path between a pair of vertices of a graph. We can define a path matrix P by the relations Pij equal 1 if there exists a path between the ith and jth vertex, equal 0 otherwise. If the ith vertex is reachable from the jth vertex, then there must be at least one path of length 1 or of length 2 or length 3 and so on up to n, where n is the number of vertices in a graph. Therefore, we can determine the reachability of all vertices by summing powers of adjacent matrix A as follows, where n is the total number of vertices. The path matrix P can be determined by setting all non-zero elements in M to 1. Figure summarizes the computations of different powers of the adjacent matrix for a sample graph. By setting non-zero entries to 1, we obtain the path matrix. Observe that second vertex is not reachable from any other vertex. The last vertex is reachable from any other vertex. A graph is said to be strongly connected if for any pair of vertices A and B there is a path from A to B and there is also a path from B to A. The graph is said to be weakly connected if there is a path from A to B or there is a path from B to A. This means that for a strongly connected graph, the path matrix does not contain any zeros. The path matrix shown in the preceding example is weakly connected because there are several zeros in the matrix. Warshall's algorithm for path matrix. The computation of powers of the adjacency matrix is a laborious and time-consuming process. Warshall proposed an alternative method which is more efficient. In this formulation, the elements of the adjacency matrix are treated as logical values. The path matrix is computed using the following recursive formula. Pij denotes an element in the ith row and jth column of the path matrix. The operators OR and AND are the logical operators. Figure lists the code for the Warshall's algorithm. It is assumed that the path matrix initially contains logical values which correspond to the entries in the adjacency matrix. Remember, character ampersand and bar represent Boolean operations and OR respectively in C++. Shortest path matrix. In graph application, sometimes we are interested in finding the shortest path between a pair of vertices. The Warshall's algorithm gives information about the existence or absence of a path between any pair of vertices. An extension of Warshall's algorithm can be used to determine the shortest path between any two vertices. The shortest path algorithm uses a recursive relation by finding minimum distance between a sequence of vertices. In essence, it computes the sum of weights wik and wkj and compares these with the weight wij. If wik plus wkj is found to be smaller than wij, it is used in the next step of computation. In order to ensure that zero entries in the adjacency matrix are not considered as minimum values in a computational step, all zero values are initially set to a very large value, which is referred to as infinity. The code fragment for computation of shortest path is listed in figure. A temporary array Q is used to store results of computations. First, the non-zero elements of the weight matrix W are copied into Q. Then, the zero values are set to 32,000, which represent infinity for the purpose of computation. It is assumed that graph is directed and that weights are non-negative values. N represents the number of vertices in the graph. Click here to watch the computation of shortest path matrix for the sample graph. The graph can be generated interactively. Linked list representation of matrix. We have seen that matrix representation has the drawback that insertion and deletion operations on a graph are not efficient. Further, matrix representation would be wasteful from storage viewpoint if a matrix is sparse. Strictly speaking, we say that a graph is sparse if it contains fewer than n log n edges, where n is the number of vertices. An alternative representation that uses linked list is more efficient for the sparse graph. In the linked list representation, there are different ways of showing relationship among the graph elements. A common approach is to use a linked list for a set of vertices which are adjacent or neighbors of a given vertex. Thus, in general, if there are n vertices, the list representation would consist of n linked lists, one for each vertex. Further, in order to provide access to each list, each vertex must be accessible by a head pointer. The set of linked lists is referred to as adjacency list. Consider, for example, the graph shown in figure. A cross in the link part of a node represents a terminal node of a list. The order of edges in a list can be different. For example, in the first linked list vertex, D can also precede vertex C. The operations of insertion and deletion of edges can be easily performed on the linked list representation. A new edge can be added by inserting tail node in the relevant linked list. An edge can be deleted by removing a node from the list. However, insertion or deletion of vertices is quite complex. In order to remove a vertex, we would not only need to delete the entire linked list corresponding to the vertex being deleted, but also remove all the edges in other lists which are linked to the vertex. This would involve scanning of all the linked lists to find if there is an edge to be deleted. List-based implementation of graph. In order to implement a graph using a list approach, we define two classes called vertex and graph list. The class vertex specifies the structure of a vertex. The specification for the class graph list is shown in figure. It is composed of an array of pointer v, which stores head pointers for each of the linked lists, and it includes the following methods. Add vertex to insert a new vertex to the graph. Del edge to remove an edge from the graph. Add edge to insert a new edge between a pair of given vertices. Get vertex to return the index number of vertex. Display to print the graph. Click here to run interactive demonstration for list-based implementation of a graph. Traversing graphs. In traversing a graph, we visit every vertex to extract information contained in vertices and edges. It is ensured that each vertex is visited only once and that no vertex is left out. There are two standard methods for traversing a graph. These are referred to as depth first search and breadth first search. As with trees, we can use recursive or iterative procedure for traversing a graph. The iterative procedure uses auxiliary data structure such as stack and queue to store vertex data as the graph is traversed. The saved information is then popped and processed in appropriate sequence. Sometimes we use special terminology to identify the processing step. A vertex which is to be pushed to a stack or queue is said to be in ready state. When the vertex is placed in the stack or queue, it is said to be in wait state. Finally, when the vertex is popped off, it is said to be in the processed state. Obviously, all visited vertices are in the processed state. We now examine the algorithms for the depth first search and breadth first search. Depth first search. In depth first search, we start with some arbitrary vertex, say x, and process it. Then, we push all neighbors of x, say x1, x2, x3, onto the stack. We pop the stack to process x1 and push all neighbors of x1, say x11, x12, x13 onto the stack. This procedure is continued until all vertices are processed. The vertices that are processed are marked as visited. The algorithm for depth-first search consists of following steps. Step 1. Initialize all vertices and mark it as unvisited. Step 2. Select an arbitrary vertex, push it onto the stack. Step 3. Repeat step 4 and 5 until stack is empty. Implementation of depth-first search algorithm. In order to implement the depth-first search algorithm, we define a class which includes the graph traversal algorithm together with the methods for creating and displaying a sample graph. Figure shows the structure of the class named GraphList. It uses two external classes called vertex and stack. The graph itself is implemented as a linked list. Observe that the class includes following private members: a pointer array vertex of size max, which holds pointers to the graph vertices; an array vi of logical values which shows whether or not a vertex is visited; a stack sk, which is used to handle vertices in wait state. The class methods are as follows. Add vertex inserts a new vertex into the graph. Add edge creates a new edge between a given pair of vertices. Disp prints a linked list representation of graph. DFS implements the depth-first search algorithm. Push ADJ handles vertices which are in wait state. getIndex is an auxiliary function to obtain index of a given vertex. Click the button to run the interactive program for the implementation of depth-first search algorithm. Breadth-first search. In the depth-first search algorithm, we first descend down the graph and then scan vertices sideways. In the breadth-first search, this order is reversed. We first traverse the vertices widthwise and then depthwise. As before, we select an arbitrary vertex, say x, of the graph. We process x. Next, we process all neighbors of x, say x1, x2, x3. Also, we push the neighbors of x1, say x11, x12, x13 onto a queue. Next, an element is removed from the queue and processed, and all of its neighbors are processed. This process is continued until all vertices have been processed. Observe that in breadth-first search, we use a queue rather than a stack. Recall that adding an element to a queue is called enqueuing, and removing an element is called dequeuing. The algorithm for breadth-first is as follows. Step 1. Initialize all vertex to mark them as unvisited. Step 2. Select an arbitrary vertex, add it to queue. Step 3. Repeat steps 4 to 5 until queue is empty. Step 4. Remove an element from the queue. Process the element and mark it as visited. Step 5. Insert all neighbors of the processed element into the queue. Step 6. Check if any vertex is left unvisited. If so, repeat step 2 using an unvisited vertex, otherwise exit. Consider the graph shown in figure. It shows the breadth-first traversal path in broken arcs. The numbers refer to the order in which the graph is traversed. Figure tabulates the steps involved in traversing the graph. Observe that the order in which the vertices are enqueued is arbitrary. We can push the vertices beginning from left to right or from right to left. Sometimes the vertices are sorted in ascending order before being pushed onto the queue. Naturally, each of these procedures would yield a different traversal path. Briefly, the steps are as follows. A is enqueued and dequeued. A's neighbors D, C, B are enqueued. B is dequeued and processed. B's only neighbor E is enqueued. C is dequeued and processed. C's neighbors F and G are enqueued. D is dequeued and processed. D's neighbor H is enqueued. E, F, G and H are successively dequeued and processed. Click the button to watch the visualization of BFS algorithm. Implementation of breadth first search algorithm. In order to implement the breadth first search algorithm, we define an interface class named GraphList. The specification and structure of the class is as shown. It uses two external classes called vertex and queue. Vertex defines the structure of graph vertex. The class queue is used to hold temporarily the vertices which are in wait state. The main class consists of the following methods. Add vertex inserts a new vertex into the graph. Add edge adds a new edge between a given pair of vertices of the graph. Disp shows adjacency list of the graph. BFS performs the breadth first search. NQADJ is an auxiliary function that performs NQ and DQ operations in traversing the graph. GetVertex returns the index number of a vertex. Click the button to run an interactive program for breadth first search algorithm. Spanning trees. A spanning tree for an undirected graph is a subgraph which includes all the vertices but contains no cycles. A graph can have several spanning trees. Figure shows a sample graph and some of the associated spanning trees. Observe that all trees contain the same number of vertices as in the original graph. Further, all trees have same number of edges. It can be shown that a graph with n vertices has n raised to power n minus 2 spanning trees. We can create spanning trees in several different ways. One simple method is to remove all edges that form cycles. When the number of vertices is very large, this approach may not be feasible. We can use graph traversal algorithms to generate various kinds of trees. We can create spanning trees by using depth first search algorithm. During the traversal, we can mark edges associated with the visited vertices. After the search is completed, the marked edges will form a spanning tree. This tree is sometimes referred to a depth first search spanning tree. Likewise, we can create a breadth first search spanning tree. Minimum spanning trees. Spanning trees can also be built for undirected weighted graphs. As before, there can be a large number of weighted spanning trees. However, there is at least one tree with the least possible summation of all edges. This tree is said to be minimum spanning tree. The minimum spanning trees are useful in many real-life applications of graphs. Telephone network provides a good example. The network can be configured using a minimum spanning tree so that all receivers are linked together with minimum length of cable. Another example could be linking of a group of islands connected with bridges so that total bridge span is minimum. The minimum spanning trees can also be used to determine air routes between a number of cities so that all cities are linked together with least travel time or lowest travel cost. In order to determine the least cost or shortest path for a graph, two important algorithms have been proposed. These are named after their inventors and called Kruskals algorithm and Prim's algorithm. Both provide efficient methodology but differ in their approach. Kruskals algorithm. The Kruskals algorithm was discovered in 1956. In this algorithm, the edges of an undirected weighted graph are scanned one by one. At each step, an edge with the least weight is picked and added to the corresponding vertices of a graph. If an edge creates a cycle, it is dropped. The algorithm can be implemented by pursuing the following steps. Step 1. Remove all edges from graph. Step 2. Arrange edges in ascending order of the weights. Step 3. Pick the smallest edge and add it to graph. If the new edge creates a cycle, reject it. Step 4. Repeat step 3 until all vertices have been processed. The resulting subgraph, which may contain fewer edges, would be a minimum spanning tree. Consider, for example, the undirected graph shown in figure. The edges and the weight are tabulated in next figure. The action column shows whether an edge is added or dropped. This figure shows the minimum spanning tree built by using the Kruskals algorithm. The thick lines represent the tree. The total path length of the tree is 10 plus 23 plus 30 plus 40 equal 103. Note that edges BD, AC, CE have been rejected because they form cycles when joined with other pre-selected edges. The edge BD, for example, is dropped because it produces a cycle with edges AB and AD, which are already selected to be the part of spanning tree. Kruskals algorithm is classified as a greedy algorithm because it immediately selects an edge with the lowest weight. It is an efficient algorithm for building minimum spanning trees. It can be shown that for a graph with n vertices and m edges, the running time of Kruskals algorithm is O(m log n). Click the button to watch a visualization of Kruskals algorithm and to print a tray. Prim's algorithm. Prim's algorithm is an alternative method for creating minimum spanning tree. As the name implies, the algorithm was proposed by Robert Prim in 1957. Unlike the Kruskals algorithm, which makes selection of edges, the Prim's algorithm picks vertices. Briefly, the algorithm proceeds as follows. Step 1. Select an arbitrary vertex. Mark it as visited. Step 2. Repeat steps 3 to 4 until all the nodes have been examined. Step 3. Find an unvisited vertex which is connected to any of the visited vertices and has the smallest weight. Step 4. If the edges do not form a cycle, add it to the tree and mark the selected vertex as visited. If the graph is not connected, then the algorithm would produce a spanning tree for the connected components of the graph. Consider, for example, the weighted graph shown in figure. We use Prim's algorithm to create the minimum spanning tree. The result of examining different vertices is shown in figure. The vertex A is selected as the initial vertex to be added to the tree. Figure shows the minimum spanning tree for the graph. The edges of the trees are shown in thick lines. If n is the number of vertices and m the number of edges, the Prim's algorithm has running time of O m plus n log n. Being a logarithmic, it is quite efficient. De Castro's algorithm. We have already studied that a path matrix can be used to find the shortest distance between any pair of vertices in a directed weighted graph. The algorithm, however, does not provide the details of the shortest path between a given set of vertices. De Castro's proposed an algorithm which generates a trace of the shortest path. The algorithm has many useful applications. For example, it can be applied to find the shortest driving distance between cities connected by roads. De Castro's algorithm works like the Prim's algorithm. It begins by selecting an arbitrary vertex and proceeds outward to cover all vertices. Unlike the Prim's algorithm, however, De Castro's algorithm repeatedly computes the distance between a source vertex and the vertex being examined and selects the sequence of edges which yields the smallest summation. This process is continued until all the vertices have been examined. By storing the information about the vertices and edges selected, it is possible to create the shortest path between any vertices. The implementation details of the De Castro's algorithm can vary depending on how the information pertaining to the vertices and edges is stored and updated at each step. Click the button to watch the working of De Castro's algorithm. The visualization also creates a trace of all steps involved and generates the shortest path between a selected pair of vertices. Topological sorting. We have seen that vertices of a graph can be listed in several ways by using different traversal methods. A special arrangement of vertices of a directed graph without cycle is termed as topological order. In this arrangement, if an edge is directed from a vertex A to vertex B and an edge is directed from B to C, the list ABC is termed as topologically sorted list. Essentially, every successive vertex must follow a predecessor vertex in the sort order. In general, there can be several sort orders. For example, if there is a directed edge to C from both A and B, then the topological order can be with ABC or BAC. Topological sorting has several applications. For example, in certain course offering, some courses may be prerequisites for other courses. A sort order would list the order in which the courses can be taken. Another example of topological order is the scheduling of tasks that must be completed before others can be started, such as in an assembly line. There are several algorithms for performing topological sorting. In one simple method, a vertex which has no successor vertex is chosen. It is added to list, and all edges that end at this vertex are deleted. This process is repeated on a next vertex that has no successor, until all the vertices have been added to the list. The result is a sequence of vertices which would be in topological sorted order. Consider, for example, the directed graph shown in the figure. Note that it does not contain any cycle. We can apply the preceding algorithm to generate a topologically sorted list of the vertices. Since E has no successor vertices, we select E and add it to the list. Also, we delete the edges that terminate at E. At this stage, the list contains only E. Next, we choose D, which has no successor, and add it to the list. The edge terminating at D is deleted. Now the list contains vertices D and E. Now the vertex C has no successor, so we choose C and add to the list, which now consists of vertices C, D, E. Since edges from B and A to C are deleted, we can select B and A and add them to the list. In this way, we end up with the list BACDE, which is the desired topological sort order. Figure diagrammatically shows sequence of vertices with broken line. The edges of the original sample graph are also pictured.